welcome everyone to the first session for today on the topic of causality. Wow, that sounds important. We have 4 wonderful talks lined up for you today. So without further ado, let us welcome the first speaker, Mohammad Reza Badri, who will talk to us about methods for bounds in the instrumental variable model. Mohammad, please.
So, hello everyone, thank you for being here. My name is Mohammad Reza Badri from EPFL, and I'm going to talk about sharp symbolic bounds in instrumental variable model. So, let's start with a simple example. Assume that we have a new treatment, and we want to know if this treatment is good or not. So, we denote 2 variables d and y. Variable d shows whether the patient received the treatment or not. And variable y denotes the score we give to the condition of our patients as the outcome variable. In order to continue, we need to talk about potential outcomes. By potential outcomes, we mean the outcome of the patient if he was under treatment or not. We denote these potential outcomes using y1 and y0. And we assume that there is consistency between our realized outcome and our potential outcomes. So now we can define our treatment effect as the difference between y1 and y0, and we aim to find the expectation of this treatment effect over our population. So the problem is we can only observe one potential outcome at each time for each individual. And that makes it hard to calculate this average treatment effect. And one easy way is to just try to calculate the difference over the treated and untreated population. But the problem is, as you can see in the slides, this average treatment is not equal to this thing we just find usually. And the problem is there might be an unobserved confounders between our treatment and our outcome. So another idea could be that we can use random treatment on the patients, and which is impractical and not a good thing to do on our patients. So we use instrumental variable. Assume that there are L different doctors, and we assign each patient to these doctors completely random. And also we assume that each doctor can affect the outcome only through the treatment. Using these assumptions, we can call Z, which denotes the assigned doctor, as the instrumental variable. This instrumental variable helps us calculate the average treatment effect by creating variations that are not caused by our confounders. So now we talked about instrumental variable. Now we are going to talk about our hidden and observed variables. We have potential outcomes in the left side and our observed variables on the right side. And we want to distinguish these two using probability laws. First, we have counterfactual law, which is a joint distribution over all potential outcomes. And we use vector Q in order to simplify its presentation. And also, we have observed law, which is the joint distribution over our assigned doctor, the treatment, and the realized outcome. And also, we use P to denote the conditional probabilities, which is shown in this slide. So now that we know that our vector Q is hidden to us, but we can only see the observed law with vector P, so we need to find the relationship between these two. And this relationship is completely characterized using this proposition. Each equality is necessary. We can just derive these equalities using just marginalization over hidden potential outcomes and using our assumptions. And the inequalities are true also because Q should be a distribution. So, As you can see, every equation is linear in terms of P and Q, so we can easily formulate this in linear, we can linearly formulate these restrictions. We call matrix M the projection matrix, which projects our counterfactual data into our observational data. So we can see that there might not be any Q compatible with these restrictions. If that happens, we can say that our IV assumptions were wrong. So we have a problem that we want to check whether there is a Q that is compatible with these restrictions or not, and we call this problem the falsification problem, as it can only falsify our assumptions, it cannot prove them. And if there was a Q, we can see that it's not necessarily uniquely identified. So instead, we try to partially identify our average treatment effect. We do this using an upper bound and lower bound, which are derived by using compatible Qs. Also, we can write average treatment effect as the inner product of our Q and some coefficient vector C. So now we can, everything is linear, we can write our problems in linear formulation, in LP formulation. Our falsification problem becomes just a feasibility check, and our average treatment effect is a maximization and minimization over our feasible region. So we can use just LP to solve these problems, but the problem is we should run this optimization each time, and our aim is to find the answer which is completely in terms of P. That brings us to a sharp symbolic characterization of our solution. By symbolic characterization, we mean that we want to write the solution in closed form in terms of our observational law. And by sharp, we mean that our solutions are exact. In the average treatment problem, we want our bounds to be tight and also attainable over compatible Qs. And in the falsification problem, we want all of our conditions to be sufficient and each one to be necessary, so we don't want duplicated conditions. And here's an example of what I mean by symbolic bounds. And as you can see, there are several advantages of using these bounds and inequalities. We can see that which probability, which observation exactly affecting our bound. And also we can use this complete characterization in order to, for example, construct estimators and other tasks. But there are also disadvantages, and the most important disadvantage of this is we can see that, as we can see in the table, the number of expressions grows exponentially. But the thing is that the thing that is more unfortunate is that the runtime is growing super exponentially. So our aim is to first try to solve the problem and find the number of expressions and characterize them, and second, improve the computational cost that was in previous papers. So in order to do so and find symbolic bounds, the main route is to dualize the problems. If we dualize our problem, we can see that our objective is linear in terms of P, and our conditions are completely independent of P and Q. So also, our feasible region is a polyhedron, and we can just find the max. We know that for a polyhedron, its maximum and minimum amounts are attainable at its extreme points. So we just need to enumerate the extreme points of this polyhedron. In order to do so, I'm just going to give an example to show the proof idea we used. In this slide, this is a projection matrix for binary instruments and binary outcome. And pink rows are the rows that are associated with Qs which have different potential treatments. As you can see, for example, Q0001, the first indexes are our potential outcome, and the second indexes are potential treatments, and in all these rows, the second indexes are different. And for a point in our polyhedron, such as V, for a vertex, for a point V in our polyhedron, we try to, the point is there should be some gray rows in my slides, but they're not visible here. So there are some gray rows that are active for that point, those rows attain equality for that point. And we use the intersection of these pink and gray vectors as the signature matrix for our points. And by using just a column-wise OR over our signature matrix, we get the signature vector for some point V. And it turns out that if V is an extreme point, its signature vector must follow a specific pattern. And also, conversely, if a signature for a point follows those patterns, its associated point should be an extreme point. And also, we can construct its extreme point in linear time. So there is a bijection between these valid signatures and the extreme points. So we can just work on enumerating these signatures, and then we can convert them linearly into the extreme points we wanted. And by doing so, we find out that the number of expressions and terms in our bounds is actually exponential. And also, we can find these bounds in time linear in terms of the number of expressions, which is optimal. So we can solve this problem in the best time possible. And also for non-binary instrument variables, we provide a lower bound on the number of expressions we need, which grows exponentially with log of n times n. So for simulation, we can see that our model, which is shown by red line, is growing exponentially and is linear in the logarithmic chart. But the previous approaches require super exponential time. This occurs because of the fact that generic enumeration methods used to iterate over all subsets of our conditions. And here we have 4n squared conditions, which means that so it's the number of its subsets should be super exponential. So generic enumeration methods fail. They need super exponential time. We follow the same approach for the falsification problem. Instead, in this problem, our feasible region is a cone, and we just want to characterize its extreme rays. And by doing so, we again derive the same results and exponential terms and etc. But you might ask, so why do we need these symbolic bounds if they are always exponential? The important things about these bounds is that they give us the structure of the points, and some problems can be solved better using just the structure without enumerating all and generating all the terms. So, for example, the problem we mentioned earlier that we used to solve using LP can be solved in time complexity of n, which is definitely faster, much faster than LP, without requiring to enumerate all exponential terms. So the main takeaway is that for sharp bounds and inequalities, the exponential cost is necessary, we have exponential terms, and this is the price for sharpness. But also, although the exponential terms are unavoidable, we can eliminate the computational overhead. And also, there are many related problems that can be solved using the structure of the points we discovered. Thank you. Any questions?
Great. Are there questions for the speaker? So while you're thinking, I will ask the first one. So you've talked about the IV model. There are some models that are similar to the IV model, like the Bell inequality graph is very similar. It's basically bijective. But also there are these seemingly simple hidden variable DAGs where things are very sad, like the triangle graph, like they've enumerated all the inequalities there. It was a huge number. They manually reduced it to some smaller number up at perimeter. And so how much of this technology transfers to arbitrary hidden variable DAGs, do you think?
I'm not sure about that. We didn't think about that, but we'll try to think about it in our future works.
Okay, but is there anything you could say about the kinds of graphs, that, like the kind of structure you would need for this stuff to work well? Because IV has certain stuff to it that makes this work, right?
I'm not sure.
Okay.
So perhaps generalizing a bit less far away your results. Have you thought about what happens if your treatment variable is not binary but can have more than two states?
Yes, we actually have solved that problem, also solved that problem using a different approach, and we are working on generalizing the instrumental variable.
Okay, thank you. Looking forward to that.
Let's thank Mohammed again. And our next speaker is Panis Masiakos, and he's going to talk to us about learning digraphs in linear SCMs.
So, hi everyone, I'm Panos. I'm a fifth-year PhD student at ETH, and today we will be talking about learning causal graphs that may contain cycles from data generated via linear models with sparse input. And this is a joint work with my advisor, Marcus. So I will start with a motivating example. Let's say that we have a data set consisting of daily stock returns. And in this context, the stocks are basically the nodes of the graph that we want to learn. So our goal is to learn some edges between the stocks that represent the causal influence between them. And we relax the typical assumption for acyclicity that exists in causal discovery by allowing for cycles. Now we will see an overview of causal discovery methods by dividing them into two categories. The first one is combinatorial, that includes constraint-based methods or score-based combinatorial searches, and continuous optimization methods. The first ones have a solid theoretical background, but are typically not scalable to graphs of 1,000 nodes. And then for continuous optimization methods, those they have introduced the acyclicity constraints, like the one from node tiers, that typically makes them more scalable, but causal identifiability only holds under certain assumptions. For cyclic graphs, the combinatorial methods inherit the properties from above, But here in the literature for continuous method, there is a gap. And in essence, there does not exist a continuous description for graphs with cycles. So this is where our work comes in, and we propose a constraint enforcing absolute stability. The methodology we propose is scalable, and our identifiability is established under non-Gaussianity assumption. So I will first talk about what we mean by stability. So the data generating model that we assume is a linear structural equation model. And for those who don't know, I will explain it. So we have, in the context of the example that I explained with stocks, we have a causal graph. The nodes are the stocks. And in the SEM, we have exogenous input S that in this example could represent, for example, the news that happen in the market and affects individual stocks. So then, via the SEM equation, the observed data X are generated with the following rule. So for each node, the value is computed as a linear combination of its parents plus noise, which makes more sense when we have acyclic graphs, but it's a bit counterintuitive having X on both sides of the equation when we have cyclic graphs. So for this reason, there is also an iterative interpretation of the linear SEM. So we can imagine the SEM as starting from a zero vector and then iteratively applying the SEM rule with a constant exogenous input S. And at some point, we might reach the equilibrium of the observed data. And this equilibrium for acyclic graphs, it exists trivially because the adjacency matrix is nilpotent. And for cyclic graphs, this equilibrium exists only when we have stability. And stability here means that the spectral radius of the adjacency matrix is less than 1. And so under this assumption, our goal is to learn the causal graph B from data X. However, stability alone is not enough for identifiability. What we mean by identifiability, for those who don't know, is whether we can distinguish the ground truth graph from the observational data distribution. So if we had the universe of all directed graphs, we would not be able to distinguish the ground truth, because there could be 2 or more graphs generating the same data distribution. The same, unfortunately, unfortunately holds for stable graphs. And now looking at identifiable graphs, the first result was lingam. So for direct acyclic graphs and data generated via linear non-Gaussian SEMs, we do have identifiability. More recently, the same result was proven for graphs with contractive cycles. These are graphs that have cycles whose product always has magnitude less than 1. So given this situation here, if we could impose somehow contractive cycles in our optimization, we would be good to go. But this is a combinatorial constraint and rather a bit harder to impose. So our solution lies somewhere in the middle. We impose absolute stability that enforces both stability and contractive cycles at the same time. Note that these two properties in general are different, and none implies the other. So formally, the absolute stability constraint is promoting the spectral radius of the entry-wise absolute B to be less than 1. So we now formulate our continuous objective. The first terms are from prior work It's the Laplacian negative log likelihood that promotes input sparsity. Then we have a regularizer for sparse graphs. And then is our contribution. The first term penalizing, in essence, the spectral radius of absolute B when it becomes larger than 1. And the second one enforcing the graph to not have self-loops, which is another assumption from prior work. Now, speaking about complexity, the first two terms are the most heavy, nd squared and d cubed. And the rest of those are of less complexity, particularly because we approximate the spectral radius with the Perron-Frobenius power method. And this makes the constraint faster than the typical cubic complexity of the acyclicity constraint. So the total complexity is dominated by the first two terms, still cubic, but in practice faster than other continuous methods, as we will see in the experiments. So moving on to experiments now, we first see some synthetic data. We have some time series data for graphs generated from nodes ranging from 20 up to 5,000 nodes and data with 1,000 time steps. We have 5% input sparsity and we compare against 13 baselines. Out of them, most of them fail, as we will see. So analyzing a bit the baseline, the first is our methods called stable spin. Then we have some methods that work with acyclic data. The first two, they softly enforced acyclicity, so we can still use them for cyclic graphs. The third one would still find a DAG, so it will make errors. Then also two other methods that allow for cycles, but only disjoint ones. And the rest of the methods, they can discover cycles. So closest to our assumptions are these two, which also assume sparsity in the input of the SEM. And also related are these four that assume non-Gaussian input. The rest have different assumptions and are expected to not perform very well in this scenario. So here we see the results. On the first plot, our metric is the normalized structural Hamming distance, which is in essence the percentage of edges that you make wrong. So lower the better. We see that most of the methods fail even in small graphs. And Spinsvar has a very similar performance to ours, except if we look at the plot below, in terms of runtime, it's much slower, especially for larger graphs. So our focus will be large graphs in the next experiment. Here we have static data, nodes ranging from 1,000 to 10,000 nodes. And here we increase the sample size to 10,000 samples, still 5% input sparsity. And we will not see any of the other baselines because they time out, except the static counterpart of Spinsvar, which is called the Sparse-RC. So we see that it's slightly less accurate in terms of NSHD compared to stable spin. But after 5,000 nodes, it times out. And the timeout here is 10,000 seconds. Stable spin achieves a 5% error on 10,000 nodes, which is quite good. So now moving on to a real data experiment, more like an exploratory experiment. In the context of the example that I showed you, we took stocks. We have the daily log returns from 100 stocks from the US, EU, and Swiss markets. We have 5 years of data, daily data, and we tested for non-Gaussianity in the data. So here we see the result of stable spin, the adjacency matrix. Annotated, you may see the 5 largest cycles found by stable spin. And we may observe some patterns in the adjacency matrix. One of those is that the edges cluster in economic sectors, while the algorithm is totally agnostic of the sector of the stocks. Then we also have some mostly intra-country edges. This you cannot see here because I don't have the countries annotated. And the edges are mostly positive, meaning that the stocks move along the same direction. So here in the same experiment, we wanted to compare stable spin with SpinSvar. And for this reason, we executed the experiment over 16 rolling windows. And we wanted to see whether the cycles found by the algorithm occur in other windows too, or whether the cycles are stable along the execution of the algorithm. So looking at the first plot, I will explain it by an example. For 0.2, it means how many cycles exist in at least 20% of the 16 rolling windows. And for SpinSvar, this is 0, so no cycles repeat, while for stable spin, some cycles repeat themselves over the windows. So stable spin has more persistent cycles, let's say. And then we see below the length statistics, we see that SpinSvar typically discovers many cycles of quite large length, which is a bit counterintuitive since SpinSvar is supposed to be an acyclic method. But the way the acyclicity is enforced is as a soft regularizer, so it still recovers cycles. But the way the acyclicity constraint is formulated with the exponential matrix, it has a coefficient 1 over factorial, and this penalizes less the long cycles. So some cycles still pass. So that was what I wanted to show you. A key takeaway of this work is the continuous constraint for absolute stability that we proposed and guarantees identifiability. Of course, it's not necessary, but only sufficient for identifiability. Given this constraint, we formulate stable spin, our continuous optimization objective, that gives us a scalable methodology that can learn graphs up to 10,000 nodes and learn some interesting patterns in the stock market. Thank you.
Great. Questions for the speaker?
Thanks a lot for the nice presentation. I have a question about the identifiability result. So last year in ICLR, there was a paper characterizing the equance class for linear models with non-Gaussian noises and cycles. So I'm wondering how that is connected to your identifiability result, because to me, you're not comparing with that result here.
So if I'm correct, I think it's the paper that I cited here, but this one is from UAI, not ICLR. So
no, there was another work in ICLR that they are actually characterizing
the equivalence classes.
Equivalence class even with the latent variables. So it's not. I think here is you are assuming that there is no latent, right?
Exactly. Yeah,
so
we
to
assume.
Me,
well, I'm not aware of this paper, but to my understanding, it sounds quite relevant to this. So when for general directed graphs, we can characterize the equivalence classes by looking at cycle reversals. So when you make cycle reversals, you get equivalent graphs. But if you assume that the ground truth has only stable or contractive cycles, then among the equivalence class, it's only that one that survives. So that gives you identifiability. So in essence, it's the same result. We are not proving something more than that here. We're just using this result to impose a constraint, in essence.
I see. There's also another work last year. Okay.
Was there a question in the back? Yeah, I think, yeah. I'm just trying to go in order. Yeah, go ahead in the back.
Hello, thank you for your interesting talk. I have a question about your optimization functional. I noticed there are some lambdas in there. And so I'm wondering about if there are theoretically optimal choices for those lambdas, or if there are things you do to select them in practice that tend to work well.
Yeah, good question, thank you. No, there are no theoretical analysis for those. We just manually chosen those by looking how much they penalize the loss. We tried overall to have, so if we're looking at the numerical loss at each epoch of our algorithm, we try to balance the losses. So they are not of very different magnitude. And that was the only thing we did.
Okay, great. Yours?
Yes, so thank you for your talk. I was wondering your stability criterion. That looks to me a little bit more conservative than it needs to be in the following sense. You rule out self-cycles, right?
Correct.
But in real-world systems, suppose there is some kind of underlying continuous system which gives rise to these equilibrium distributions that your SEM models, or there could be very fast timescales. You typically have these self-cycles. And basically when you do your learning, you're asking the question like, could I have this kind of, here it's written your iterative interpretation.
Mm-hmm.
Once you allow for self-cycles, you can realize more SEMs. So,
that's correct.
Have you looked into more, or let's say more flexible notions of stability here that allow for self-cycles? Because there are results in systems theory, linear systems theory, which give an kind of analogous condition, which is not about spectral radius, but it's a different condition. But it could enlarge the class of SEMs that you can learn.
Maybe are you talking perhaps about time series and structural vector equation models? Or just
well,
static
kind of
data?
abstracting away from that, you just ask the question, could there be some kind of temporal model which realizes those SEM equations written at the top?
Yeah, no, we haven't looked. That's quite interesting,
Okay,
actually.
we can take this offline. Yeah.
Absolutely.
I have one quick question before we stop. I noticed that you need the spectral quantity to be less than 1, but then I also noticed you approximate it. So might it be the case that your approximation says it's less than 1, but the actual quantity is bigger than 1, and then you have a problem? Like, how do you deal with that?
Yeah, it's actually heuristic. It's we cannot tell whether the real graph is stable. We just
Okay, so but doesn't that explode your procedure sometimes, basically? Like if you have a really if an adversary picks a really annoying graph, like your heuristic will tell you everything is fine, but things are not fine, and you explode, basically, right?
Yeah, that's a good point. We could have an analysis on how well the approximation is.
Okay.
We did not. Yeah. Thank you.
Right. Let's thank the speaker. Great. Our next speaker is Ziazian Wu, and she will talk to us about coarsening bias due to variable discretization. Thank you.
Okay, hi everyone. My name is Xiaxian Ou. I will start my second-year PhD study at the Emory University. I'm honored to be here to present our work, Coarsening bias from variable discretization in causal functionals. This work is joined with my advisor, Rosie Nabi. At first, I want to give you a big picture. Don't worry about the notation. Let's just see the roadmap of my project. in causal inference, people often work on the important functional involving the integration over density of continuous variable. We call the original target. It takes the form like this theta q. But estimating density is hard. Even though statisticians have developed a lot of fancy methods, in practice, researchers in applied work study, they often take the simple way. They directly discretize the continuous variable into categories and use the finite summation. So we call the Causal target. They take the form like the theta h. So when we use this Causal target, could we really get what we want? And if not, where does this bias come from and how could we fix it? So in this project, we just do a simple correction in this functional, which gives us the bias Causal target. That's the tilde theta h. Now, let's start by looking at the original target. Let me introduce you to common causal settings. Assume we have one binary treatment with two levels, A0, A1, one mediator, one outcome, and the covariance. Then we use Q to collect all the nuisance functions. If you are interested in the mediation effect, you can look at the left model. You will care about the nested potential outcome, and after some assumptions, you will have the identification formula per psi q. Similarly, for the right one, in the from-door model, if you are interested in the average potential outcome, after some assumptions, you will have the identification formula gamma. So you can see per psi q and gamma q, they share the same component, theta qc. It is the function of c, and in this theta, we integrate the outcome regression over the mediator density. This is exactly what we will care about, we will focus on, and sometimes I may directly call it theta for simplicity. What makes this integral challenging? We could notice that the outcome regression and the mediator density, they are evaluated in the different treatment levels. That means this integral cannot be simplified further. So when the M is continuous, it's hard to do the density estimation. There are several ways in the statistical area we can get around it. Like we could use the numerical computation, but it's computationally demanding. Or we can also use tricks like sequential regression or probability weighting to avoid the density estimation. But sequential regression requires correct specification, and probability weighting may give us some extreme unstable weights. So people can also try to use the advanced estimators like one-step estimator or TMLE. But in applied work, it may be a little complicated for the researchers to use it. They directly discretize the continuous mediator into the category one, especially when the categories have the specific clinical meaning. So let's take a look at the process of discretization. At first, we need to define a discretization rule H, which categorizes the continuous mediator into the category 1 tilde m with several key levels. And the big K is the support of the mediator within each bin. WK is the bin weights. We can take the BMI as example. Let's look at the BMI bar. We divided the continuous BMI into 4 intervals. Then, mapping them into tilde m 1, 2, 3, 4, they are corresponding to the clinical categories. After we have these bins, we can rewrite the targets as the Causal target from the original one. We replace the outcome regression by the within bin specific mean, and we replace the density by the probability. After we have this in the raw data, if we want to estimate the nuisance function and use this Causal estimator, do we still recover the original one? So we can can write the difference between theta HQ hat and theta Q, then decompose this total difference into two parts by adding and subtracting the theta HQ. The first part is the statistical estimation error. It arises because we estimate the nuisance function. And the second part is the coarsening error. Currently, let's only focus on the coarsening error. To make the theta HQ and the theta Q more comparable, we rewrite the original target theta Q also in the same being form. So within each being, we average the outcome regression over the mediator probability under A0. That gives us the yellow block. So we will have this form of original target. The blue block shows the cosine target we have mentioned before. So we can see the difference between these two is exactly the outcome term. Now let's check this within being difference more carefully. The overall coarsening error is the weighted average of this within being difference. And here I don't want to show you much detail about the proof. I just want to give you an intuition. By the Taylor expansion, we can write these within being differences by the outcomes loop times the within being mean mediator mean shift and plus the second order term. Here, the within being mediator mean shifts is exactly the difference between mediator within the same beings but under different treatment levels. To give you a better understanding of it, I will show an illustration from the simulation. Here, we don't have any estimation, so I will generate a very large sample size from the known DGP and use the true nuisance function. And I will discretize the mediator using the equal frequency. That means I need to keep the balanced sample size within each being. So we can see the mediator density in different covariance levels and in different treatment levels. The two colors shows two beings. The vertical line marks the within being mean, and the distance between two vertical lines in the same column with the same color shows the within being mediator mean shifts. So after knowing the source of this coarsening error, let's check the rate of it. At first, under the smoothness condition, we can get the within being difference is bounded by the being width, and after aggregating across all beings, the overall coarsening error is bounded by the maximum of being width. And now let's take the statistical estimation error together. Assume we have a fixed discretization rule and assume the Euro statistical estimation error has the root n rate. Then this error is a function of the sample size. The coarsening part is bounded by the largest being width, and that means the narrow beings can reduce the coarsening error. We can think it more deeper. If we have large sample size, then we can afford to use more beams. And if we use the equal width beams, then we can get the coarsening error is bounded by the 1 over Kn. That means we can use more beams to make the coarsening error, to reduce the coarsening error. But do we have to only rely on making more beams to reduce such error? Could we just improve the cosine function node itself, even in small k? So yes, that's exactly what we do here. Here we just make a small correction in the outcome term. We evaluate the outcome at the within being mean here under the treatment level. This gives us the debiased functional. We have the idea here because this century could make the first order term average out, and then we only have the second order term in the within being difference. So this correction is nice because it works for any discretization rule, even under the small k. A similar argument for the rate. Here, I just go through it quickly. For the overall coarsening error, it is bounded by the square of the maximum of the beam width. And also take the statistical estimation error together. The root n part remains the same, and we improve the coarsening error from the first order term to the second order term. Also, use the sum equal within beams example. The overall coarsening error is improved from 1 over kn to 1 over kn squared. After this theoretical story, we need to evaluate different estimators using finite sample size. Here we use the same DGP and the same setting as the previous simulation, but we need to estimate the nuisance function using GOM with the correct specification. And here we work on the plugin estimators in the mediation models. We can see the red one is the coarsening estimator. The bias decreases when the k increases, but within the same k, the bias doesn't change honestly when the sample size increases. That means this bias is mainly driven by our coarsening part, and our debiased estimator, this blue one, it can substantially reduce the bias. So this result supposes that our correction is very useful. Besides reducing the coarsening bias, could we do something more to help with the statistical estimation bias? Generally, one-step estimator is attractive because it has good properties, like it allows for flexible machine learning models, and it has asymptotic normality. It is robust to model misspecification. So here we can write the one-step estimator for the quotient target and also for the original target. We have these two. They look complicated, but we only need to pay attention to the blue one. That is the quotient functional, and the yellow one, this is the original functional. But unfortunately, we cannot have the one-step estimator for the debiased one because the debiased functional is evaluated in the exact point. That means it's not pace-width differentiable. And we cannot have the one-step estimator for it. But we can play with what we already have and have some heuristical one-step version. Like for the first one, we can start from the one-step estimator of the quotient target and just replace the quotient functional by the debiased functional. And the second one, we can start from the one-step estimator of the original target and replace the theta by also by the debiased functional. But be careful, these two, they are not the real one-step estimator. They're just our heuristical version. So currently, we have two previous plugin estimator and the 3 one-step version. We can compare them under different model misspecification conditions. Here, the plot is crowded, and we don't need care much about it. If you are interested in it, you can check in my paper, and we can discuss more later. Here, I just want to highlight some results. We found that one-step correction only works for reducing the statistical estimation bias, but it doesn't work for the quotient bias. And then we found that our debiased plugin estimator performs well under the correct model specification. So that means for the practical use, our debiased plugin estimator is simple and is attractive. It is a good option to consider if people want to use the discretization. We also have some extensions in our paper. I just go through it quickly. The first one is we can replace the exact point evaluation using some smooth kernel, then the DBIOS functional is piecewise differentiable, and we can have the following one-step estimator. And second, we also try to evaluate the estimator on a different discretization scheme, like the equal frequency, equal wins, and the predefined threshold. And the third one, we also extend our work to two other mediators using the same sintering strategy. Finally, let's look at the real data application. Here, our data is based on the frontal model. We just want to check the effects of the mobile stroke unit here on the third mouse MRS score. Here, people have used this data in the application work. They directly discretize the continuous mediator. And also, the following paper has tried the one-step estimator and the TMI estimator. Here, we only compare the plugin estimator. We compare the Causal plugin estimator, the DBIOS plugin estimator, and also the plugin estimator based on the sequential regression. We just use it as a comparator. Here, we just found the DBIOS estimator more closely agree with the version of sequential regression. So overall, I just want to give you 4 takeaways. The first one is that the discretization, they may change our causal target, and we may have some causing error. So we can use the wisdom bin symmetry to improve the causing error from first order to the second order. And the one-step correction can help us with the statistical estimation bias, but it does not work for the causing bias. Finally, our DBIOS plugin estimator is simple as effective. So if you are interested and want to talk more, welcome to my poster session today in the afternoon. And I'm happy to have any questions. Thank you.
Okay. Are there questions for the speaker? Yes.
Hello, and thanks for the nice talk. So you're interested in mediation analysis, but all I saw was like just a treatment effect, and I'm wondering if you have looked into it all to like natural direct effect or natural indirect effect with this discretization method.
Actually, here we are not focused on the effect. We are focused on the just one estimate like this one. We can use this one to calculate the natural indirect effect or natural direct effect.
Okay, so maybe I misunderstood. What is the effect of the second order correction that you're making when you're doing this, especially like the indirect effect? Because I imagine you would have different values for mediators that are in separate bins and different corrections and so on.
Here we only care about one estimate. This is the one specific potential outcome, and we can compare 2 outcomes to get the causal effect. Here we just focus on one outcome, one potential outcome, and then you mean the different what? You mean this average or wisdom bin average?
Well, I mean the effect essentially.
But here we don't talk about the effects. We just mention when you want to calculate the mediation effect, you will need to know this potential outcome. Then how to calculate this potential outcome?
Okay, maybe we can take this offline. Thanks.
Hey, thank you for a nice talk. Could you go to the... oh, sorry, somebody else. Go ahead. Go ahead. Ask your question.
Yeah, go ahead. Yeah. But you're next, yeah.
Thank you for your great talk. here.
Sorry.
Sorry, we're flipping things around a little bit.
Can we extend to your method to more generalized causal graph structure? So you have mentioned some graph structure where you have two ordered mediators, right? So, for example, if you have a large number of mediators, can we easily vanish the first order Taylor expansion term, or are there any difficulties in that situation?
Yes, good question. We have this extension in the supplement, but actually when we extend to the two-order mediator, we found it is not very easy to find the to make the first order term average out. So I haven't tried, but I think maybe it may be complicated if we want to extend more to more mediator.
Okay, thank you.
Thanks for a really nice talk. Can you go to slide 16? Or I think it was the one which has your numerical experiments. Maybe it's the previous one. Oh, yeah. So over here, as n increases, it looks like your confidence intervals stop covering the truth. Is that just a statistical estimation bias that's unavoidable in this case, or is that something else?
You mean which case? Or you mean the blue one?
Oh, I'm sorry. So like, you can see there's like some remaining bias as
you mean this here?
Yeah. Is that the statistical estimation bias? Or?
Actually, this is not the confidence interval. This is just the arrow. This is just the variance of the arrow here.
Yeah. Okay. Sure, but I'm just saying, as n increases, it seems like the bias is not going to zero, right? Like
yes, because we still have the second order term.
Okay. All right. Thank you.
Okay. Well, I have a question. So, two-part question. So, first of all, you talked about influence functions for the front door and for the indirect
here,
effect
I only
functional.
work for the mediation.
Okay. So, all right. So, first question is, how does your analysis change if I do like arbitrary influence functions? And second is, so you do mediators specifically. So mediators appear in these influence functions in particular ways.
Yeah.
But for example, I could have a continuous treatment I could discretize, and treatments appear in this influence function in a different way than the mediator. And how does that change your analysis for correction? Have you looked into that?
Yes, I think here our study is limited because we only focus on the simple way, like one binary treatment, just one mediator, and here the influence function is based on the mediation. But I think I just want to show this correction, this idea of correction, that we can find the first order bias and then to correct it. This is just a high level, I think, the idea of this. But I think it is hard to directly to apply in a specific case.
Okay, thank you.
Thank you.
Okay, let's thank the speaker. And our last talk of the session will be by Jong-Hwan Kim, and who will talk to us on connections between causal discovery and logical deduction. Thank you.
Good morning. My name is Jong-Hwan Kim. I'm from Seoul National University, and today I will present our work, Don't Test What You Can Deduce, Causal Discovery with Logical Inference. So let me start with the main message of this work. So when the size of conditioning set is large, conditional independence tests, or CITs, can be unreliable in finite samples. And it makes lots of issues during structural learning. So to tackle this issue, we propose quite a simple idea. Before running each statistical test, first ask whether its answer can already be logically deduced from the previous test results. So we integrate this idea into PC algorithm, resulting in possibly fewer conditional independence tests and competitive structural accuracy. So first, a little background. So causal discovery aims to recover cause and effect relations from observational data. And one prominent line of work is constraint-based causal discovery, including the renowned PC algorithm. These methods systematically perform conditional independence tests to recover the underlying structure of the data. PC algorithm, for instance, starts from a complete undirected graph, and whenever it finds that two variables are conditionally independent, then it removes the corresponding edge. So in this example, once we find that x and y are independent given z, the edge between x and y is removed. The difficulty is that these statistical tests are not perfect with finite data. PC algorithm proceeds level by level, which means it gradually increases the size of conditioning set. And any test can be noisy in real world, but in general, testing becomes much more difficult as we condition on more variables. And importantly, a single force independence can remove a true edge. And since later tests depend on the current graph, this error can propagate through the rest of the structured learning, and it will have a negative impact on the subsequent tasks, such as estimating the causal effect from the learned graph. So, in that sense, we would like to avoid unnecessary statistical tests, especially at higher levels. So the natural question is, what can we do to tackle this issue? So consider this simple graph on the right-hand side. So at level 0, PC is trying to learn its graph. And at level 0, it performs marginal tests between pairs of variables. So from these tests, it obtains both independence and dependencies. For example, it already knows that y is independent of z, and while y is dependent on x and x is dependent on z. Now PC moves to the level 1 queries. And right now, the algorithm is about to ask whether x and y are independent given z. But before actually running the new test, look at what we have, what we already know from the previous test results. We already have all three relations shown here. And these previous results are not isolated pieces of information. Actually, you can use the logical relationship between conditional independent statements, which is governed by graphoid axioms, so that we could, and they already imply that x and y must remain dependent given z. So in that way, we can determine the answer without looking at the data again. In other words, no new CIT is needed. So this motivates the central question of our work. So why execute a fragile high-order CIT if its answer is already logically entailed from strictly lower-order CIT's results? Our key idea is therefore to deduce before testing. So traditionally, a CIT result is mainly used as a signal for whether an edge should be deleted or not. We instead treat these CIT results not only as edge deletion signals, but also as logical premises for future queries. If a new query is logically entailed, then we skip the CIT and take the result. And only when deduction is insufficient do we fall back to the original CIT. So to do this, we provide Deduce, an logical inference engine for deducing higher order conditional independence outcomes. So its input is a target conditional independence query together with the query history of strictly lower order test results. And this Deduce module recursively examines that query history of the PC algorithm and returns one of the three outcomes: independent, dependent, or unknown. Importantly, unknown is allowed, which means that Deduce module does not guess when the available information is insufficient. So the ingredients of Deduce modules are sound inference rules derived from faithfulness and graph reductions. These rules allows us to infer higher order conditional independence outcomes from strictly lower order query results. The first rule here is used to deduce dependence, and the second one is used to deduce the independence. And I won't go through every logical case written in here, but the important point is that the Deduce module recursively applies these rules to infer a target conditional independence outcome, and higher order query can be reduced to several lower order queries, and those, until we reach results already available in the query history. We then present Deduce First PC, or DFPC, which integrates the Deduce module into PC algorithm. The main idea is very simple. Whenever PC algorithm requests a CIT, DFPC just passes that query to the Deduce module, logical inference engine. If that Deduce engine can infer the outcome, then we immediately return the result and skip the CIT. But if it returns unknown, then we simply perform the original CIT. So in this case, our deduction module, acts as a filter in front of the statistical tester, rather than as an additional procedure after testing. So let me show how DFPC actually learns the graph from the motivating example. At level 0, there is no difference between PC algorithms and DFPC algorithms. Both algorithms execute the same 6 marginal CITs. And these outcomes form the initial query history that Deduce module can use at later levels. In particular, notice the 2 independence findings shown in green. At level 1, but the difference begins. A standard PC algorithm would statistically test all 7 queries listed on the upper row. But DFPC, on the other hand, can deduce 4 of them directly from the level 0 query history. So those are the blue queries. So only the remaining 3 queries actually require statistical tests. The key point is that the information collected at an earlier level is now reused to infer or replace later tests. At level 2, this effect becomes even stronger. all 3 level 2 queries can now be deduced from low-order information, including results that the deduce module itself inferred recursively. So PC algorithm performs 3 of additional CITs at level 2, but our algorithm performs just none of them. So overall, on this small example, the total number of statistical tests drops from 16 from PC algorithms to 9 for DFPC, while learning the same structure. So we also established some theoretical guarantees for this procedure. So first, with perfect conditional independence information, the Oracle tester, every outcome produced by Deduce engine is correct, and so correctness of the Deduce engine. And the second is DFPC also inherits the soundness guarantee of the PC algorithm. And the third is apparently, DFPC never requires more physical CITs than PC algorithms. And interestingly, there are some non-trivial graphs that DFPC can recover only using the marginal CITs, which is not the case for the PC algorithm. So as for experiments, we evaluated the DFPC on both Erdos-Renyi and scale-free graphs across different graph sizes and densities. We considered both discrete and linear Gaussian data, and we measured 2 aspects: structural accuracy using F1 score and structural Hamming distance, and computational efficiency using the number of executed CIT and runtime. So first, accuracy. Across those settings, DFPC is quite competitive with PC algorithm and often improves the recovered skeleton. The gains are particularly clear for discrete data and denser graphs. This is important because our goal is not just simply to perform fewer tests. By avoiding some fragile, higher-order tests, we can reduce the statistical burden without sacrificing too much on the structural accuracy. And next, efficiency. So in the linear Gaussians, in this setting, DFPC consistently executes fewer physical CITs than PC algorithm. And this reduction also translates into lower overall runtime. So even though Deduce engine performs recursive logical inference, its overhead is small enough that replacing statistical tests still gives a net computational benefit. The advantage becomes even more pronounced when the individual CITs are expensive. Here we use nonlinear data with the kernel conditional independence test, KCI. And in this regime, CIT execution dominates the overall runtime. Therefore, every statistical test we replace with the deduction becomes much more valuable. This is why the reduction in CITs translates almost directly into a large runtime improvement. So let me conclude with the main takeaway. So in standard PC, independence findings are mainly used to delete edges. But DFPC uses these findings not only as edge deletion signals, but also as ingredients for logical deduction. And by extracting more information from the test results we have already performed, we can avoid many unnecessary higher-order computational independence tests. And the result is fewer fragile statistical tests, lower computational cost, and competitive structural accuracy. Thank you.
Great. Questions for the speaker? Oh, Dan?
Thanks for the really nice talk. I think it's a very reasonable and nice idea. I was curious if you guys looked at all into how this affects error propagation in PC. So like if one of the lower level tests is incorrect, in regular PC that propagates to later tests in a certain way. And do you know how this affects the logical deduction?
Actually, we did not do some theoretical discussions on what you've just mentioned, but we already tackled that in our empirical evaluation while during the rebuttal. So we already put the empirical evaluations on that issue in our appendix. So maybe if you are interested in, then you can find the results there. Yes.
Thank you for your great interesting talk. So you seem to simply measure the reliability of a conditional independence test as the number of conditional variables, right? So, but I'm wondering whether we should do this because, for example, even when we have the same number of conditional variables, some test statistics can be, for example, clearly independent or clearly dependent or something like that. So, but yeah. I think kernel independence tests are computationally challenging, so I think I understand, but we don't have to compute the test statistics, or before we need to just determine whether we should perform independence tests, or what do you think about this? So we don't have to compute the test statistics, evaluate the test statistics, or to evaluate the necessity of tests?
Firstly, I guess in this work we mainly focused on the conditioning set size, and as some kind of a proxy for the reliability of the tests. Yeah. And actually, there might be some other factors that is affecting the reliability of the condition independence test. And as for instance, let me take an example of a chi-square or g-square test in the discrete setting. In that setting, maybe the number of conditioning, the size of conditioning set size also matters, but also the cardinality of the variables also matters. When testing the condition independence. So maybe if I could extend my work to that direction, it would be great. But in this work, I focused on the.
Okay, thank you.
Thank you. My intuition would be that this is more efficient if the graph is more sparse. Maybe that's wrong. In this Edish-Rainey experiment, did you look at the connection between efficiency versus edge probability? For example, if you drop more edges, does your algorithm become more efficient? Is this?
If it gets sparse, does the algorithm gets? Not really. I mean, yes, not really. Actually, it depends. Sometimes if graph becomes denser, there might be some more opportunities for DFPC to replace the higher order CITs. So sometimes, in denser graphs, they have become more effective in some sense, but I guess it depends. Maybe there are some other factors that we should consider, not just like the edge probability or,
Okay, thank you.
There's a question in the back as well.
Yeah, thanks, very nice idea. I have a dark past as a logician, so I have a question about the formal logic part of your talk. It looks like you're encoding the deduction problem in a propositional language. So that should be decidable unless you're doing something with weird operators. So why is then your deduce algorithm returning an unknown? Is it like you have a roof on runtime, or what? Can you give us a little bit more information about that?
About why there is an unknown here?
Yeah, so if I understand correctly, your inference engine returns a dependent, independent, or unknown.
Yes.
Given a query.
Yes. So I think it's gonna be quite long answer, I guess, but
Could take it offline maybe, because there's a bunch of other questions.
Yeah.
That's okay.
So
Okay, great.
I will be in the post session today, so I'll be happy to talk about it in the post session.
Thanks.
So since there's many questions, there is one more question on Zoom, and then maybe we could take the rest offline because we have to end. Please go ahead.
This is a question from Zoom. Why are there differences between PC and DFPC if they give the same output as mentioned in the talk?
Pardon? Pardon? Why is the difference?
In the simulated study, why are there difference between PC and DFPC if they give the same output as mentioned in the talk?
I think they're asking why there's a finite sample difference in your simulation results between PC and your modified version of PC, given that they produce the same output asymptotically.
Actually, in the finite sample, I guess, yeah, as I said before, yeah, any test can be noisy, and if you are performing more tests, then you are probably exposed to more risk of having an error, and that might have propagated to the rest of the structured learning, and it might have negatively affected the results, I guess.